Hi, I'm Ed Kohler with Extreme Networks. Thank you for having me here today to talk with you about the evolution of a particular protocol architecture that our campus fabric is based on. It's called shortest path bridging. Now, this is an evolution of a standard of the Ethernet protocol. And we've always known the Ethernet protocol to be known by an IEEE standard of 802.3. It actually is a broadcast medium. It allows multiple participants to communicate. Now, bridging, switching, and VLANs have evolved that protocol model. But at the end of the day, we really have a series of scoped flooding domains by the use of virtual local area networks. We invoke a standard called spanning tree protocol, which basically allows for loop-free broadcast domains. But realize there is no sense of a path at this level. Now, in the traditional networking model, we introduce the sense of a path by introducing some sort of Internet Gateway Protocol. And basically, the IGP, like OSPF or RIP, provides us IP path information in the network. So in the legacy model, we don't really have any sense of a network path until we introduce IP as a protocol. Now, if we want to do multicast, the ability to have the network replicate and provide things like video surveillance or IP television, we need to introduce yet another protocol known as PIM, Protocol Independent Multicast. This provides us the ability for multicast over the environment. But note how it's an overlay, and it's dependent on the actual underlying Internet Gateway Protocol model. Now, going further, if we want to divide this environment out, we need to introduce something like a virtual route forwarding environment. Now remember, a video surveillance system or something like an IP television system, those are best set off to the side so that they can become a subscriber type model to the service. In order to have VRFs, I need to peer them, and I can either peer them with the Internet Gateway Protocol, or I can peer them with the use of BGP, the Border Gateway Protocol. Once I have these private IP VPN communities and I want to bring them across the carrier network, I introduce the MPLS protocol stack. And here, MPLS has different services such as Layer 2 and Layer 3 IP VPN. This is the traditional stack that we've always accepted in the networking model. And we have to realize that all of this really exists because of the core reason that Ethernet has no sense of a path. Around 2000, 2001, we started working on a protocol known as provider-based bridging, provider-based transport. And that is an IEEE standard known as 802.1 AH. And 802.1 AH introduces something very unique. First of all, it introduces the notion of instantiating a path at the Ethernet level. And it also introduces something known as a MAC addressing hierarchy. There are a number of limiting factors to how large you can build a traditional Ethernet domain without dividing up the network with IP. And those constraints are due to, first of all, the scope flooding domains that we talked about, but also it's due to the fact that I have one flat MAC networking space. It's all one hierarchy. A router's MAC address is the same as a server's MAC address, is the same as my laptop's MAC address. So there's no sense of a hierarchy. What happens in this environment with 802.1 AH is we actually introduce the concept of a MAC hierarchy between the subscriber edge, or the client edge, and the network service core. The lower level hierarchy is where the actual subscribers access the cloud, and those are known as the client MAC hierarchy. They're normal Ethernet addresses, as I said earlier, a router's address, a switch's address, my laptop's address. In the middle of the network, we have another hierarchy called the BMAC hierarchy. And that BMAC hierarchy allows me to actually transport information across the core of the network and keep the actual client edge in a totally separate plane of connectivity. Not only does this provide inherent security, but it provides an inherent path mechanism within the network itself. Now, in order to complete the concept, let me draw some switches within this framework. And we'll mesh them together. Because remember, we have the sense of a path at an Ethernet level. I no longer need spanning tree because I'm no longer dealing with loop-free flooding domains, and I don't have to maintain those. So now we have a network that we've introduced, and we have several switches in the core, and we have switches at the edge at a division called the user-to-network interface. And all switches connected in the middle are connected by network-to-network interfaces. So the network-to-network interfaces operate at the backbone MAC level, and at the user-to-network boundary operates at the CMAC level. This is how the hierarchy works. And it's used to create a tunneling method known as MAC in MAC. MAC in MAC encapsulation basically provides the transport mechanism for me to move information across the cloud. And I can draw a very simple representation of this. But before we do, let's put some labels on these switches. So we'll say that the starting point is switch A. We have switch B, switch C, switch D, switch E, and switch F. So now we have these paths across the network, obviously the NNI links. We have labels for the switches. And now what happens is we have a MAC address that is generated at the edge of the cloud. And that MAC address sends an Ethernet frame, just a normal Ethernet frame. Remember, this is all standards-based technology. This is 802.1 AH. So at the client edge, we have a device or a switch. It could be an Extreme switch. It could be a Cisco switch. It could be Juniper. It could be any vendors. As long as it generates a valid 802.3 frame, it will transport that traffic. So this is an open industry standard. Now, once the Ethernet frame ingests into the user-to-network boundary, it enters into the actual NNI domain. And this is where Fabric Connect lives. At that point, MAC and MAC encapsulation works as follows. The actual 802.3 frame becomes payload. Then we append a destination, a source, and there's another field called an I-tag field, which I'll talk about shortly. But in reality, what happens is we append the destination information into the destination address. And in this case, it's going to be switch F. The source, obviously, is going to be switch A. Now, this is all a priori knowledge. This is programmed into the switches because we need to do that. This is a universal labeling format. We don't swap headers. Think about in this model over here, the legacy model. When we see that happen, we have routers. And these routers work on a hop-by-hop fashion. Now, looking at that, each router does a compute cycle, and it swaps headers. Therefore, I have to have time deltas to account for that compute cycle. I also have a protocol, link state advertisements, things of that nature that move between these to coordinate them. There's propagation delay associated with that. But because I'm swapping the headers, if I do have a failure in a given network path, in order for an alternate router to participate, I need to calculate and consider all of these propagation delays. And this is one of the reasons why networks are notoriously slow to converge, particularly the more meshed and complex they get. And the reason why we're doing that is because we're swapping headers at each point. Therefore, we need to converge that network manually through compute cycles. Now think about it. If I'm going to ship you a package via Federal Express, and I ship it from one end of the country to the other. There's a fairly good probability that a plane will get delayed, perhaps a truck will break down, a driver will be sick. FedEx doesn't ever call me and say, hey, we're here in Missouri and we had a truck breakdown or a plane delayed or breakdown. We need reroute information as far as what you want to do. Of course not. They have logistics. They have a priori knowledge. They know of alternate trucks. They know of alternate flights and alternate planes. Same concept here. By not switching the labels, I can have a failure in any point in the network, and the downstream switch will automatically know how to reroute the information through the network infrastructure. So this MAC and MAC capability is pretty powerful, the fact that we point to the end destination and we do not swap the headers. However, if I have a customer here, and let's say they have 5,000 MAC addresses, and I have another customer here, and he has 5,000 MAC addresses, well, now I'm into a situation where I have 10,000 MAC addresses on the core of the network, or on the edge of the network, but in the middle, I only have the number of MAC addresses that I have, and in this case, it's 6, because the BMAC hierarchy is separate. So notice what happens here. We have this vast reduction in MAC explosion within the core of the network, which gives us very good scale in the network infrastructure. Now, there's a couple things that I'd like to point out here, though, is that this is a provider-type service model. So if we put in a separate switch, a different client hanging off the edge of the network, and we say that that has 5,000 addresses as well, obviously we can scale, but we can no longer tell the difference between client A and client B. This is where this field comes in. This is called the I-tag field. Now, a little bit of story here. When we started running into limits on the current VLAN count, which is 4,096, there were two paths that were created. One was to create a standard called 802.1 AD, which is Q and Q. And it works, but there's some limitations to that because I can give a parent queue to one client or subscriber, and they will use 10 VLANs within that group. I can give another parent queue tag to another, and they might use 100. But there's a lot of wasted service space. And the reason why is because we've got 12 bits for the parent queue tag, and then 12 bits for the child queue tag. So you got 4,096 instances of 4,096 instances. What we did in an alternate version with 802.1 AH is we introduced the concept of something called the individual service identifier, or the I-SID. The I-SID uses a 24-bit field. And that 24-bit field, allows us for a numerical count of 16,777,215 in a flat service space. That's an immense amount of scale, an immense amount of capacity. Now, in that instance, what I can do is I can start to assign I-SIDs to different customers. So I can say perhaps I-SID 1000 will be for customer 1, and then I-SID 2000 will be for customer 2. Now I have the ability to tell customer A from customer 2, and the I-SIDs basically provide that complete separation between those subscribers or those clients. This is another inherent part of the security. Now notice I have not talked anything about IP, because we're not using IP to establish the service delivery. This is all happening over Ethernet. But we still have one challenge that we have to handle. That is what happens when I put an alternate client boundary. So let's say that we have somebody hanging off switch E, and they are part of I-SID 1000 as well. And let's say they have 5,000 MAC addresses. What do? I have 3 points of presence How do I service ARP? How do I handle MAC learning? How do I handle multicast activity? Well, this actually took a bit of time for us to think about. In around 2004, we came up with an answer for that. And we developed basically a method of putting more information into the destination address. Think about it. Multicast is probably one of the most difficult paradigms in networking. It's a destination address, which means it's never topologically significant. I can't say where the source is. It can't be represented because it's a destination address. So we chose to do a number of things. We created a multicast addressing format that embeds further information into it. So this multicast BMAC is used to provide further information to the data plane so it can actually do further process called Tandem replication. And Tandem replication works at the data plane level against certain pieces of information that we insert. The first thing we do is we add a multicast identifier, and that happens to be 03 in the shortest path bridging standard. Now, most times when an Ethernet switch in the legacy model see a multicast frame, they say, oh, or a broadcast frame, they say, oh, I'm just going to flood it everywhere within the VLAN. We don't do that. When one of our nodes sees the 03, it automatically says, wait a minute, there's further information that I have that is in this frame. The next thing we embed is something called the nickname, or the shortest path source ID. I'm just going to write a SPID, shortest path source ID. This provides the source of the actual multicast or broadcast traffic. The last field provides the actual I-SID. So an important thing to realize about I-SIDs is they're always a directional graph tree. So in this case, we're going to take everything from perspective A. Everything I've done up until now has been what's called non-directional graph. But now we're going to pick a point in topology and say we're going to look at things from the perspective of node A. This is what we call directional graph theory. Directional graph theory is always based on directional graph trees. I have three participants in I-SID 1000, switch A, switch E, and switch F. Therefore, I have three perspectives of directional graph trees, from switch A, from switch E, and from switch F. Now we're going to handle directional graph trees from the perspective of switch A. Let's say that this subnet, the yellow subnet, I-SID 1000, is a particular IP subnet. And let's say that IP address, or the IP subnet, is 10.10.10.0/24. And we have a network address of 10.10.10.10. We also have a node over here that's 10.10.10.12. And now 10.10.10.10 wants to talk to 12. The initial thing that happens is it sends out an address resolution protocol request. It sends out an ARP. It says, I want to talk to 10.10.10.12. Now, ARPs are broadcasts. That fits one of the classes because this tandem replication works against a certain class of traffic, and we call that BUM, broadcast, unknown, which is the MAC learning processes, and then also multicast, as in the case of true IP multicast. Now, in this scenario, we have an ARP coming out from 10.10.10.10. I have three service points. 10.10.10.12 could be at either one, or it could actually be local with 10. So when the ARP actually enters the cloud, what happens is A says, oh, wait a minute, that is a broadcast request. Therefore, I'm going to embed certain information. I am going to embed the fact that my source, I'm sending it out, is going to be the shortest path ID of A. And then the I-SID value is placed in the back frame. So now I have all the information in the multicast BMAC address. Now any switch in the middle can look And as this broadcast propagates across, it follows the I-SID path. At this point, B would look and he'd say, wait a minute, I'm actually traversing, I don't have any service points, but I-SID 1000 is traversing me. I need to replicate. And it knows by this information embedded directly in the data link. So it will automatically replicate, send the information out. All parties receive that broadcast. 10.10.10.12 can respond and then use the unicast service path. So that's how tandem replication works within our fabric. So you can see these I-SIDs are pretty cool. They're very powerful. They're nothing but Ethernet switched paths down at the lower layer. But we need a coordinating control plane to make all of this work. We certainly don't want to have a network operations center where everyone's programming this up. That's where another evolution to the protocol happened, and that's the introduction of a control plane protocol that we invoke called I-SIS. Now, I-SIS stands for Intermediate System, Intermediate System. It was the original protocol for connectionless routing within OSI, so it's a fairly ancient protocol. Many people ask us, wow, that's pretty archaic. Why did you select that? Well, it's extensible. Now, when you think about it, look at OSPF or look at RIP. It's what is termed as a monolithic protocol. It's designed to route IP version 4. That's all it does. As a matter of fact, when we started with IPv6, we needed to create separate versions of RIP, separate versions of OSPF in order to actually do this. That's because they were all based on dependence of the IP protocol themselves. OSPF doesn't even work without IP. So in this instance, we selected I-SIS because it does not need IP. It was created before IP became the predominant protocol. Therefore, it uses and moves information by the use of layer 2 packet data units. And what is a layer 2 packet data unit today? Well, of course, it's Ethernet framing. We have really very little use of any other alternate layer 2 PDUs in today's industry. So this becomes a very good, ideal protocol to start to move information. And the goal is to use this protocol to program the actual data plane. So we're not invoking I-SIS to work as a traditional routing protocol as we would over here. If we took I-SIS and put it in this layer, it would be just like any other routing protocol, and it will be using the hop-by-hop swapping paradigm and everything else. Nothing changes. It's just a different routing protocol. Here, we're using it as a control plane. And the best way to draw this is with a very short diagram. Down below, we have the 802.1 AH data plane. And the data plane itself, you can see, works quite autonomously. And it handles failures. It handles replication. It handles all of the requirements needed to establish path behaviors. So notice how we no longer need IP to establish our topology. We no longer need IP to move data across the network. So 802.1 AH becomes our data plane. I-SIS becomes our control plane. And I-SIS programs a link state database. And that link state database resides in each and every switch in the Fabric Connect network. This provides all of the a priori knowledge required to handle the data plane. Now, the reason why I say a priori is, remember, we have no a priori knowledge here. We have to discover it through convergence. By having the link state database and a priori knowledge of all alternate service paths, any failure can happen within this, and we will fail it over under 200 milliseconds, many times far under that. And the reason why we can do that is because we have this a priori link state knowledge base that is programmed by I-SIS into the data plane. Now, I-SIS obviously uses PDUs, but it moves information by the use of something called type length values. Type length values are just that. It's the type field which says this is the type of information I'm giving you. And that could be topology. It could be layer 2 services. It could be layer 3 services. Could be multicast. The length is obviously the amount of information I'm going to provide you. And then the value itself, which is the value of the information I'm giving. Now, these type length values are created to move, first of all, topology information. The first thing we build is the base, so that A knows it can get to F through alternate paths across the network infrastructure. And if any network were to fail, for instance, B in the middle, B would automatically know to use the alternate path through E. So this becomes a very critical thing, and it's one of the key reasons of why we have so much resiliency within the fabric architecture itself. Now, these type length values can represent services as well. We can represent layer 2 services, which we've been primarily speaking about here. But we can also represent the representation of layer 3 services, IP. IP subnets can be represented. And even though we can service these IP subnets with Ethernet switching services, we're not using IP routing to interconnect them. Going further, we can actually create IP VPNs. IP VPNs allow me to use VRFs and tie those VRFs to I-SIDs. Now, the I-SIDs provide the peering rather than doing the peering through the protocol fat stack that we have on the other side. Now, once we have IP VPNs, we can also introduce multicast services. Multicast services allow me to run and deliver video surveillance, IP television. And the secret here is we use I-SIDs to do that. We communicate that information through values, and then we build the I-SIDs out to support that multicast. And that actually requires a separate whiteboard. Now, we also have the ability to extend the model to actually talk about IPv6, type length values to service IPv6 and IPVPN. Now, a couple things I want to talk about right now is I want to compare what we've accomplished against the actual FAT protocol stack that we talked about earlier. We have type length values for layer 2 services, I-SIDs. Those actually replace VLANs, and they replace layer 2 services up in MPLS, virtual private LAN services. We have layer 3, global routing table. We can replace the IGP. We no longer need that, remember, everything's happening through Ethernet. We have the IPVPN, the concept of tying and peering the VRFs together through I-SIDs. We replace layer 3 IPVPN. We replace the use of BGP and or IGP if I'm going to peer them with an IGP type protocol. Multicast, whether unconstrained within the global routing table or constrained within the IPVPN, replaces PIM. IPv6 is not even represented in this model. We'd need a separate stack in order to service IPv6. So you see the extensibility of the model. You also see what happens is we collapse, because there's another shortcoming to this model over on the left-hand side or right-hand side, is the fact that we have top-down dependencies in this model. If anything in the lower portion of the protocol stack fails, the whole thing collapses like a house of cards. And it takes a long time for these networks to converge. Notice what happens here. I have a very short, flat stack, and it's all mutually, atomically independent of one another. What this means is that networks for healthcare, for instance, hospital networks that need 24/7 uptime with massive change windows, can start to shrink those windows down or even eliminate them. They can go in through the course of the business day, make major changes to the infrastructure, and they will not affect any of the other services because of this horizontal and independent service construct. We just program the link state databases. We can introduce a VRF in the middle of the day, peer them together with an I-SID, light up multicast in the middle of the day. You'd never be able to do that with a traditional architecture. You'd have to bring the network down, You would have to have outage time, you'd have to have rollback strategies, all sorts of things to deploy that new VRF with multicast enablement. That's an incredible evolution. And that's one of the reasons why we can offer the severe OpEx benefits. We can actually take an OpEx model and reduce it sometimes on the order of 10. That's fantastic. Thank you for your time, and I appreciate it.